I want you to just picture a classic, retro, 32-bit pixel adventure game.
Oh, like the kind you'd play on an old, chunky, handheld console.
Yeah, exactly. You've got your little pixelated hero on the screen, swinging a sword, cutting down grass tiles, maybe throwing a boomerang. It's a project called Sword Slasher. And on the surface, it really just looks like this pure, charming throwback to the 90s.
It definitely leans hard into that whole aesthetic, you know. You see the health potions, the chainmail armor, those little damage numbers popping up when an enemy takes a hit. The visual language is just incredibly familiar.
Right, but here's the thing. If you peel back those pixelated graphics and actually look at the underlying architecture, Sword Slasher is not a nostalgic relic at all.
Not even a little bit.
No, you are looking at a cutting-edge, data-driven engine. This little indie project has quietly solved some of the most frustrating bottlenecks in modern software development. I mean, we're talking memory bloat, astronomical AI API token costs, and even that really notorious problem of AI hallucinations.
Yeah, the contrast there is really what makes it so fascinating. The developer is basically using a retro game format as this like Trojan horse to test a highly optimized data structure.
And that actually brings us to our mission for this deep dive.
Right.
Because this conversation is tailored specifically for you, the listener. We know you love gaining deep technical knowledge quickly without getting bogged down in useless jargon or, basic definitions.
Yeah, we're skipping the filler.
Exactly. So today, we are looking through the raw code, the developer notes, and the configuration files of Sword Slasher to unpack how this developer completely re-engineered data storage. They built an AI-integrated relational database that is so efficient the entire game, and I mean the database, the engine, the assets, all of it, runs inside a single offline HTML5 file.
And to really understand the mechanics of how they pulled that off, we have to look at the foundation of the engine. It's built on a custom format they call the Medium Format Database, or MFDB, version 1.31.
Okay, MFDB.
Right. And specifically, we need to look at the file format they created to replace standard JSON, which they named BEJSON.
Right. So let's talk about standard JSON for a second. It's the backbone of almost every web application today. But anyone dealing with massive data sets knows it has a really severe weight problem.
Oh, absolutely.
Because if you have an array of, say, 1,000 item objects, standard JSON requires you to repeat the object keys for every single entry.
Which creates a massive footprint. I mean, if you have 1,000 items, the V8 engine, or really whatever JavaScript runtime you're using, it has to parse the word name, the word category, and the word attack bonus 1,000 times.
Just over and over again.
Exactly. And the memory bloat isn't just about the file size on your disk, It's about the parsed object tree in the RAM. Every single repeated key string takes up heap memory.
Because the object itself requires those hidden dictionary mode allocations, right? Just to track the keys and their pointers.
You got it. The structural text ends up consuming way more memory than the actual integer or string data that you're just trying to store.
Okay, so BEJSON circumvents this by completely severing the structure from the data. I was looking at the configuration files we have, and at the very top of a BEJSON file, there is just a single array called fields.
Yes. You define your keys exactly once.
Right. You establish that, okay, column 0 is item id, column 1 is name, column 2 is category, and so on.
And then immediately below that, you have a values array. And this is just an array of arrays. It's a pure data matrix.
Well, it's just the raw info.
Right. So the entry for a health potion is literally just a bracket, then potion, health potion, consumable, health, 50,000, and then the hex code for red. And that's it. No keys attached. It relies entirely on positional indexing.
It's basically taking the organizational logic of a spreadsheet and mapping it directly into an array format.
That's a perfect way to look at it.
Like, you write the headers in row 1, and every row beneath it just contains the raw values.
Yeah.
You don't rewrite the company letterhead or the column header in every single cell of the spreadsheet.
No, because that would be insane. And they actually took this beyond just flat data storage. The MFDB architecture implements a formalized relational database directly inside this array structure.
Right, I saw that. There's a master manifest file, right?
Yeah, it's called 104a.mfdb.bjson, and it basically orchestrates the entire initialization sequence of the engine.
So that manifest acts as a really strict dependency resolver. It explicitly tells the engine, hey, load the events logic first, then the object rules, then actor stats, and finally the visual assets. It guarantees everything boots up in the correct order.
Furthermore, it enforces strict relationships across the different BJSON files. Like, if you open the actor.bjson file, which holds all the character data, you find fields that are specifically designated with an FK suffix.
Stand for foreign key.
Exactly. So a field like leveled forecac logically binds a specific enemy actor to a specific stage in the game world. Or a field like equipment weapon flag that binds a specific sword from the items table directly to the player's actor record.
So if you strip out all that repetitive structural text and you rely on just an array of arrays with relational foreign keys, the raw file size and the memory footprint must just absolutely plummet.
It's a massive reduction.
I mean, is that insane memory efficiency what allows them to bypass standard browser security restrictions?
Yes, that is the direct mechanism. Because normally, if you build an HTML5 application that needs to load separate JSON data files or images, you have to run it on a web server.
Right, because of course.
Exactly. If you just double-click an index.html file on your desktop, the browser's CORS cross-origin resource sharing protocols, they'll block the JavaScript from fetching local files from your hard drive just due to basic security sandbox rules.
Which is incredibly tedious for distribution. Like, you can't just hand someone a zipped folder and tell them to play the game or run the tool.
Right, but the sword slasher developer circumvents CORS entirely by actually compiling the game. They wrote this Python script that takes the incredibly lightweight BEJSON database, along with all the SVG vector graphics, and just stringifies them.
It just squashes it all down.
Yeah, it injects this massive, dense data string directly into the JavaScript payload of a single index.html file.
And they built a virtual file system to handle that payload, right? I think it initializes as window.mfd-bvfs.
You got it. The engine includes a database driver wrapper. So during runtime, when the game logic requests, say, the level data, the driver intercepts that request. It doesn't attempt a network fetch at all.
It just looks inward.
Right. It reaches into that virtual file system object loaded in the browser's memory, finds the corresponding string, parses the BEJSON, and serves the data. The end result is this complex, data-driven application that requires zero server configuration. One file, fully offline.
That is wild. And wait, going back to the data footprint for a second, I noticed something else in the source about database read costs.
Oh yeah, the Firebase integration?
Right, because if you were running this on a standard cloud backend, every time a user logs in and the game queries to a traditional JSON structure, it's pulling thousands of individual documents or heavy nested trees, which spikes your read operations.
Exactly. But with this setup, when they do sync to a backend, they are just downloading that one single compressed BEJS string. The sources mentioned this can lead to up to a 98% reduction in Firebase read costs.
98%. That is a game changer for indie devs paying for server costs out of pocket.
It really is. You're replacing thousands of document reads with one highly optimized string fetch.
Okay, so that offline portability and the cost reduction are huge advantages. But looking at the developer notes, this ultra-dense data structure was actually designed to solve a completely different problem, right? It was about integrating a large language model directly into the development pipeline. They built an AI assistant called the Executive System Advisor and Game Architect.
Yes. They are utilizing the Gemini API, specifically the Gemini 3.5 Flash model, to actively code game mechanics, balance combat stats, and even generate levels.
Wow.
But when you integrate an LLM that deeply into a project, API token limits and costs become a massive bottleneck. Because, you are billed based on the amount of text you feed into the prompt window.
Oh, absolutely. If you tried to pass a standard JSON database containing 1,000 items into a system prompt, the redundant keys alone would consume tens of thousands of tokens.
You would hit the context window limit almost immediately. Or, your API bill would just be completely unmanageable.
But because BEJSON is an array of arrays, the memory footprint is just a fraction of standard JSON. So the developer scripts can actually take a full, real-time snapshot of the entire virtual game database and embed it directly into the AI system prompt for literally a few cents.
It's incredibly cheap. Yeah.
Okay, but I have to push back on the architecture here for a second. Because stuffing the entire game database into the AI prompt every single time you query it seems like absolute overkill. I mean, if I ask the AI to generate a new sword variant, why does it need the coordinates of every grass tile and the stats of every goblin in the entire game? Doesn't flooding the context window with all those unrelated variables risk, confusing the AI or degrading its focus.
It seems counterintuitive, I'll give you that. But providing the complete relational schema is actually what constrains the model's probabilistic output.
How so?
Well, think about it. Large language models are essentially prediction engines. If you give them a vague prompt without constraints, the probability space for their output is just vast. Flooding the context window with the complete BEJSON database acts as an unbreakable guardrail against AI hallucinations.
Oh, I see. Because the AI can see the exact parameters it is allowed to operate within.
Precisely. Let's say you ask an isolated AI to design a sword. It might just invent a new property called magic damage, right?
Because it sounds like a good RPG stat.
Exactly. But the sword slasher combat engine only processes physical attack and defense. A magic damage variable wouldn't just be ignored, it would cause a runtime error.
It would break the game.
Yes, but by providing the full database, the AI sees the field's array for items. It mathematically recognizes that it must output an array with exactly the defined columns, mapping perfectly to the existing logic.
And the developer notes detail the specific mandates programmed into the system instructions. The AI is assigned read-only access to the MFDB v1.31 architecture.
That's a crucial detail.
Yeah. When it suggests a new item or enemy, it is explicitly ordered to output the raw code within a standard markdown block, accompanied by a file name tag on the first line. So, for example, filename.datums.bjson.
And that strict output format allows the developer's tools to parse the AI response programmatically. They just run a regex script that captures the markdown block, reads the file name tag, and seamlessly routes the newly generated array directly into the virtual file system.
And the AI isn't guessing at relationships either. Because the entire database snapshot is sitting right there in the prompt, it can see the existing foreign keys. It knows exactly which leveled values are valid and which item IDs already exist.
Right, which completely prevents duplicate keys or broken references. And they actually apply this exact same methodology to the visual assets using what they call the AI Sprite Studio.
Wait, so the AI is making the art too?
Yeah. The Gemini API isn't just balancing stats, it is generating the game's graphics. The system sends strict JSON schemas alongside the prompt, like a vector schema, for example, that demands the output be a valid SVG tag constrained to a view box of exactly 32 by 32 pixels.
Wow. And the technique they use for visual continuity is particularly clever from what I read.
Oh, the color matching.
Yeah. If the developer needs a back-facing view of an existing character sprite, the system prompt takes the raw SVG string of the front-facing view and feeds it back into the AI. And the mandate explicitly commands the model to retain the identical gradient IDs and hex color values from that original SVG.
It essentially forces the model's output probability to align with the existing color palette. It literally cannot hallucinate a new aesthetic because the required visual variables are so heavily weighted in the prompt's context window.
It's locked in.
Exactly. The combination of strict schemas and full database visibility transforms the LLM from this chaotic generative tool into a highly predictable, reliable function of the game engine itself.
It's like, okay, it's the difference between asking someone to write a sequel to a book based on a vague summary versus locking them in a room with the original manuscript, a glossary, and a strict style guide. They literally can't mess up the lore.
That is a perfect analogy.
So, okay, we have a highly efficient single-file architecture that neutralizes AI hallucinations by leveraging dense relational arrays. The file size is tiny, the token costs are minimal, the Firebase reads are basically non-existent. But there's a glaring computer science problem here that we haven't talked about.
I was wondering when we'd get to this.
Yeah, because querying an array of arrays for real-time applications is fundamentally inefficient.
It introduces significant time complexity. You are dealing with linear search overhead.
Right. If the engine uses a standard JavaScript dictionary object, retrieving an attack stat is instantaneous. You just query item, bracket, attack bonus, and boom, you have the value.
But BEJSON detaches the keys from the values.
Exactly. So if the game logic needs the attack bonus, it first has to scan the fields array just to locate the string attack bonus, determine its index position, say position 5, and then query the values array at index 5.
Which means the engine is performing an O of n linear scan just to figure out where the data lives before it even retrieves the data itself. And, if this happens once during a web page load, it's irrelevant. But in a real-time environment like Sword Slasher, the physics engine is ticking at 60 steps per second.
And the math inside that combat library is heavy. I mean, it takes the attacker's base stats, queries the weapon's attack bonus, queries the defender's base defense, adds the armor's defense bonus, runs a 60% armor mitigation formula.
It's doing a lot of work.
And it calculates a 10% critical hit probability for a 1.75 damage multiplier and factors in a level difference modifier, all in one swing.
Now multiply that by the AI library. The engine runs a continuous state machine for every single enemy on the screen. It is constantly calculating vectors, checking distances, updating states from idle to alert to charge.
Every single frame.
Every frame, for dozens of entities. The engine requires hundreds of variable lookups. So doing thousands of array scans per second to resolve column indexes would just bottleneck the CPU thread and cause the game to stutter severely.
So we're at a standstill. Standard dictionaries solve the lookup speed, but we established they create memory bloat. Arrays solve the memory bloat, but they completely destroy the lookup speed.
Right.
So how did the developer reconcile those two opposing constraints to maintain 60 frames per second?
They bridged the gap using a dedicated library called BEJSON fieldmap.ts. They built a mechanism called field map indexing that completely eliminates the array scanning during runtime.
Oh, I see how they did this. They generate a cache map at boot.
Exactly.
So when the engine initializes and loads a BJSON file, it triggers a core function. I think it's called BJSON core get field map. It doesn't map the arrays every frame. It maps the schema just once.
Correct. The function reads the fields array and generates a unique signature for that specific table structure. It concatenates the MFDB format, version like 104 or 104A, with a serialized list of the field names. And this creates a highly specific cache key.
And that just maps every single string from the fields array to its integer index position.
Right.
So it records that, okay, item is 0, name is 1, and attack bonus is 5.
And it stores that mapping globally in an object called field map cache. Because the engine relies on strict data schemas, the index of attack bonus in the items table is never, ever going to change during runtime.
So when the simulation is actually running, the combat library just completely bypasses the fields array.
The real-time logic never performs a linear scan, period. When the damage calculation fires, the engine queries the field map cache for the index of attack bonus, and a standard object property lookup for an integer is heavily optimized by the V8 engine. So the cache instantly returns the integer 5, and the engine accesses the raw data array at position 5.
And that is how they achieve O1, constant time lookup speed.
Yes, it is.
They get the rapid execution of a standard dictionary without paying the hidden memory overhead of attaching string pointers to every single data value. That is brilliant.
It really allows the core engine orchestrator to seamlessly manage everything. The terrain library, the registry library, the inventory library, and that dynamic chunk management.